So the aim of this part of today is to look at what we mean by power functions and exponential functions, and then start thinking about how we can use logarithms to get these functions, these power and exponential functions, into a form y equals mx plus c, which you might recognize as the equation of a straight line. So that's what we're aiming for. We're aiming for a straight line graph, because if we get a straight line graph, we can find the gradient of the line, which gives us m, and where it cuts the y-axis, which gives us c, and from that we can find some information about this power function. We'll look at some examples of some power functions and some exponential functions. You'll see they're nowhere near straight lines, so what we're aiming for is trying to get these to look like straight lines. In fact, this idea of getting a straight line graph applies to any type of function, but we're going to apply it particularly to these power functions. So that's the aim. So first of all, let's have a look at what we mean by these power functions. So power functions have the form y equals a to the x to the a. So some power a. So our two variables, the independent and the dependent variables, still x and y, but x is now raised to some power. So an example of that is x squared, which we've seen, the quadratic function. And we know that looks like a parabola. So that's an example of a power function. But it could be x cubed, it could be x to the 4. And if you applied it to an engineering scenario, particularly if we're thinking about gases, expansion of gases and things like that, we actually find that the powers are not whole numbers, 1.7 or something like that. So these powers, we need to be able to find out what they are. And the way to do it is to plot the graph and trying to get it to look like a straight line graph, so we can find the missing number, and we'll look at that. The other type of graph that we're going to be interested in is the exponential function. And that has the form y equals a to the x. So in other words, this time the two variables y and x, the independent variable x is the power. So we've got some constant a raised to a power x, and that's an exponential function. It's called the exponential function because the exponent, which is what we sometimes call the power, is where the independent variable is. That has a similar shape to the top one, but in that case x is actually in the power rather than the power being the base. So in the power functions, x is the base. So here's a graph of y equals x to the a. But if I change a, using the constant controller, right, this over here so I can see it, there it is. A is set at 1 at the moment. So in other words, what I have here is a graph of y equals x to the 1, or y equals x. And there it is. But if I change a, then we can see we start to get a curve, okay? Y equals x squared. I'm not quite sure why it's not showing on the other side of the graph on this particular graph plot. Something strange going on here. But you can see the curve is changing as I increase or decrease the power. So we can imagine expansion of gases or something like that. If I heat something up, so if this was temperature up here, and we're looking at the volume of the gas, then the rate at which the gas is expanding or contracting would be some sort of power function. And we would want to know what this power is, 2.6. How do we find it? Well, what we do is we want to try and turn it into a straight line graph, and to do that we need to use logarithms, which are the rules to do with powers. So let's go back to our functions, and what I want to do today really is just to introduce you to the idea of the logarithm, or remind you of the logarithm, because we looked at it last year. To investigate these functions, we use logarithms. So we need a quick reminder of what these logarithms are. And the basic rule is, if we have something like y equals x to the a, for example, some power function, then the logarithm of y equals the logarithm of x to the a. So I take the logarithm of both sides. And logarithms are to do with powers. And the laws of logarithms enable us to play around with this thing. So the laws of logarithms. In fact, what we'll do is we'll put the laws of indices and logarithms together, because they are combined. Sorry? Yeah. Far enough, Harry? So these laws, we split the page into two. We've got if we've got x to the a multiplied by x to the b, from the laws of indices, you add the powers. That becomes x to the a plus b. Because logarithms are powers, then we say that the logarithm of a times b is the same as the logarithm of a plus the logarithm of b, because logarithms are powers. Similarly, x to the a divided by x to the b would be minus the powers. So with logarithms, the logarithm of a divided by b is the same as the logarithm of a minus the logarithm of b. X to the a raised to another power, b, if I've got one power raised to another power, can you remember what the rule of indices is? You times them together, Tom, right? X to the a times b. So, and this is the useful one for us, this is really the key one, the log of a to the power b is b times the logarithm of a. We just multiply them together. And this is the important one that we're going to be using. So what we have is a situation where I've got one power raised to another power then I can turn that into a multiplication. So if I turn my power function into a logarithm, then I can actually turn the power into a multiply. So if we look back at this, y equals x to the a, here, if I take the logarithm of both sides, I've turned both sides into powers effectively. So I've got one power, log of x, raised to another power a, so I can use the law of logarithms and bring this a down and turn it into a multiply. So that means, so therefore, the log of y equal to, we have the log of, what did we have? Log of x to the a becomes the log of y equals a times the log of x. Yeah. Okay. So, and we'll expand on that next week and look at some examples of it, but what we have is a situation where we've taken a power. This is a power function, so remember what we're after doing is finding this a. We've brought the power down from being a power and turned it into a multiply by taking the logarithm of both sides. So that's easier to work with. And what we'll end up doing is plotting a graph of the logarithm of one variable against the logarithm of the other, and then we'll find that we can calculate what a is from the graph. So we'll look at some examples of this next time. We'll start at this point. I think it's chapter 30 in the textbook talks about logarithmic graphs, and the chapter before talks about turning power functions and other types of functions into straight line graphs. So if you get a chance, have a look at chapter 29 and 30 in the textbook before next week, and then we'll carry on from there. Okay?